Welcome to video 16.1a. The discussion here will focus on rate expression. This is higher level content that goes a little bit deeper into the idea of reaction rates, but it's a little bit more of a mathematical spin on things. So let's get rolling. Helium walks into a bar. The bartender says, "We don't serve noble gases in here." Helium doesn't react. In terms of accessing your prior knowledge, rates of reaction will be important and sort of as a big general overarching concept. And yes, I realize it's a bit obvious, but remembering some things that affect rates of reaction just as a general concept. The big idea for 16.1, rate expressions, which is a term we'll get familiar with throughout this video. Rate expressions can only be determined empirically, and these limit possible reaction mechanisms. The mechanisms are the step-by-step sequence of events that occur for a particular reaction. A lot of reactions are not just one step. In particular cases, such as linear chain of elementary reactions, no equilibria, and only one significant activation energy barrier, the rate equation is equivalent to the slowest step of the reaction. The slowest step will be called the RDS, the rate determining step. And the word empirically just means based upon experimental data. I have a lot of understandings here that are going to kind of work in sequence or in concert, if you will, over the next number of slides. And so I'm not going to read them to you, but we are going to work with something called K, which is different from Kelvin, which is a unit. This is called the rate constant, K. So let's look at some example reaction rate data. Fullerenes, remember those? C60 with each carbon bonded to 3 other carbons, sp2 hybridization. There is a particular form of a fullerene that can have 3 oxygen atoms kind of in a loop above attached to these 2 carbons. It actually can be oxidized relatively easily to form C60 with only 1 oxygen. It can be reduced, to form C60 with 1 oxygen plus O2. So let's look at some rate data for this actual reaction. The absorbance of C60O3 can be measured. Recall, according to Beer's law, concentration is directly proportional to absorbance. So if I track the absorbance over time of the reactant, that should go down and it should reach a point where it levels off because there's no more reactant left. And if I draw a tangent at that point, so my tangent is almost a straight line, act like it is, that would give me the rate at that moment in time. And if I draw a tangent here, that is the instantaneous rate for that moment in time. And if I draw a tangent here, that is the instantaneous rate at that moment in time. And you can see that the rate is decreasing over time. So let's look at a little bit more detail. A little bit more detail. Sorry about that. So concentration versus time is what we looked at. And if I take the tangent at each point, I actually see that if the absorbance is here and this is absorbance per minute, so like change in absorbance per minute, this is the slope at any given point on this graph. So the rate is decreasing. And these steps are determined from the tangents. And since concentration can be measured by absorbance for some molecules, I can determine the rate, and it's equal to the change in concentration of the C60O3 molecule divided by the amount of time. And this is negative because this is a reactant, and reactants will decrease, products will increase. So if I look at the absorbance versus rate, recall that absorbance is the equivalent of concentration of that C60O3 molecule. So the higher the absorbance, the higher the concentration. And at higher absorbances, there was a faster rate. And so this just sort of verifies the idea that absorbance can measure rate. And so, if the rate is proportional to the concentration, then we can say reaction rate is equal to some constant K times the concentration. And this K is called the rate constant. And this is called the rate expression. And it is the rate expression for this reaction because this reaction is only dependent upon the concentration of the C60O3 molecule. So the rate expression as a generic form is some constant K times the concentration of anything that is required for the reaction raised to some power. And I want to emphasize that M and N here are generic numbers that can only be determined through experimental evidence. They are not the coefficients from here. So this is not going to be M and N. It might be, but not automatically. So it is possible that they can be the coefficients, but they are not automatically the coefficients. And it is often the case that they are not the coefficients that are here. We will figure them out experimentally, and I will show you how we do that. So let's look at an example question. And this will bring up a word that is new to this video called order of reaction. And we'll understand what that means after the example is done. I have a reaction, hydrogen reacting with nitrogen monoxide to form water and nitrogen gas. It is shown from experimental evidence to be second order with respect to hydrogen and, second order with respect to NO and first order with respect to H2. Give the rate equation for this reaction and its overall order. So for the reaction in question, because it is second order with respect to NO, in the rate expression, the concentration of NO is raised to the second power because it is second order. And hydrogen is first order, so it is raised to the first power. Now, what that means is if I double the concentration of NO, it will quadruple the rate. And if I double the concentration of hydrogen, it will double the rate. And we'll learn later kind of what it means to be second order and first order. There's a lot more detail. This is just your first exposure to this idea. The overall order is third order because it's second order for NO and first order for hydrogen. 2 plus 1 is 3. So let's look at some example reactions. Maybe pause the video and take a look. I've got order with respect to the reactant number 1, so the first reactant, the second reactant. There's only one reactant, the first reactant, the second reactant, and here there's only one reactant. So I have the order with respect to reactant 1, the order with respect to reactant 2, and the overall order. The overall order is the orders added together. I want you to take a look at these and see if you notice a pattern. And more specifically, do you notice a pattern about the relationship between the balance equation and the order of reaction for the reactants? Is there anything significant about the pattern? And at this point, I hope you're recognizing that there is really no pattern. The pattern is that these orders of reaction do not necessarily match the balance equation. They did in the first reaction, 1 and 1, first order and first order, but here this is only first order. Here, this is first order and first order, even though this is a 2, and here this is first order, even though that's a 2. So the balance equation does not necessarily tell you the order of reaction. That is a key point here that I want to emphasize. Let's look at the units for the rate constant K. For a zero order reaction where the concentration doesn't matter, the rate is equal to K. And so rate has the units moles per decimeter cubed per second. So that means K would have the units of moles per decimeter cubed per second. So remember that rate is always moles per decimeter cubed per second. So if I have a first order reaction, the units of K must work such that my concentration units and the units for K equal moles per decimeter cubed per second. And this concentration will have moles per decimeter cubed. So that means K must be per second. If I have A squared, that means I have moles squared per decimeter cubed squared. And so in order for the rate units to work out, I need per mole times decimeter cubed per second. And I think what I'd like to do is just have you look at this, and then when we get to class together, let's go through some examples and really make sense of this rather than taking up video time. So let's look at a sample problem where we're going to calculate rate. A reaction has the rate expression rate equals K times A squared times B. The rate is given 7.75 times 10 to the negative fifth moles per decimeter cubed per minute. So notice that this is per minute. Normally it's going to be per second, but the key is it needs to be per unit time, and so we need to keep that in mind, per minute. The concentrations of both A and B are 2.5 times 10 to the negative second moles per decimeter cubed. So the rate is going to equal K times A squared times B. We know the rate, we know the concentration of A, and we know the concentration of B, so it's a matter of substitution. And then this will help us talk about the units. So here it is solved. I kind of threw it at you all at once here, but let's talk our way through it. We're going to substitute the values into the rate expression. So I have 7.75 times 10 to the negative fifth moles per decimeter cubed per minute equals K times the concentration of A squared times the concentration of B. So K is going to be this value here divided by these two values with that squared. So I have 7.75 times 10 to the negative fifth moles per decimeter cubed per minute divided by 2.50 times 10 to the negative second cubed, because these are both 2.5 times 10 to the negative second. This was squared, this was to the first power. And then my units, moles per decimeter cubed, are also cubed. So for my units, I have per minute, and that doesn't change. There's nothing to cancel it. On the top of my equation, I have moles per decimeter cubed, and on the bottom of my equation, I have moles cubed and decimeters to the negative ninth. So that means these moles cancel, and that mole cancels to moles squared. These decimeters cubed cancel, and this becomes negative 6. And so that means I have moles to the negative square, negative 2 times decimeters to the 6th power. Because if I'm dividing by negative 6, it's equal to 6. If I'm dividing by second, it's to the equivalent of negative second. So my units are moles to the negative second times decimeters to the 6th power times minutes to the negative first power, like per minute. I don't have this memorized. I don't memorize this unit. I do this math and I work out the units so that I don't need to memorize it. I don't have any of the units memorized for rate constants because I know I can figure them out. And if you need another example in class, I'm happy to show you. Now let's look at graphs. We've got a zero order reaction, which is a bit counterintuitive, but zero order reactions do actually occur. A zero order reaction occurs when the rate is not dependent upon the concentration. I'll give you an example on the next slide. And so the concentration of the reactant just simply goes down at an equal rate, no matter what the time is, until it's all gone. And so that means if I change the concentration, I'm not able to change the rate. And this is unique. This is not true for most reactions, but there are some reactions where this is true. And an example is ammonia on a platinum catalyst to form nitrogen and hydrogen gas. The rate depends on the number of ammonia molecules that can attach to the surface of the catalyst, and the surface of the catalyst is very small relative to the total number of ammonia molecules. So increase in the concentration of ammonia will not make the rate go any faster, because there just isn't enough space on the catalyst to handle all those extra molecules. So the reaction order is 0. If I have a first order reaction, the concentration will decrease over time and it will level off as the rate gets slower. And so higher concentrations have a higher rate, lower concentrations have a lower rate. And the rate slows down because the reactants are being used up, and so therefore the concentration of the reactants decreases and the rate slows down. And this would be rate equals K times some concentration A. For a second order reaction, rate equals some rate constant K times A squared, and the rate constant will be independent for every reaction, will have its own rate constant. As I go through time for a second order reaction, concentration of the reactants will decrease pretty quickly at the beginning, and then it will level off. But here, and this looks very similar to the graph from the previous slide, but it's a little different. But this graph is a lot different. In the previous graph, I had linear scale, so if I doubled the concentration, I would basically double the rate. But here, if I double the concentration, I'm going to do it approximately from here. I think this is about double. If I double the concentration, the rate goes up by 4 because it's double squared, which is times 4. So if I double the concentration, the rate increases by a factor of 4 because of the rate expression, which is determined experimentally, which is still coming up soon. Let's compare graphs. Concentration versus time. 0 order, first order, second order. Rate versus concentration. 0 order, first order, second order. Take a look at those and kind of make sense of them. Now, in terms of determining order of reaction, we're going to use something called the initial rates method, where we vary the starting concentration of the reactants one at a time, and we measure the initial rate of the reaction. You are going to do this in an experiment using the colorimeter. So, if I have a 0 order reaction with respect to some reactant A, if I double the concentration of A, there will be no effect on the rate. That's what happens for a 0 order reaction. But if I double the concentration of A and the rate doubles, then I know that it's first order. And if I double the concentration of A and the rate quadruples, I know that it's second order. So let's see if we can use this table and look at some experimental data and figure it out. Here's some experimental data. I have 5 different experiments where I vary the concentration of A and B in some generic reaction, and I'm able to calculate the rate. So if I keep the concentration of B the same and I double the concentration of A, I want you to notice that this is doubled the concentration. What happened to the rate? The rate doubled. So that means it is first order with respect to the concentration of A. So I'm using experimental data to figure this out. I kept B the same, so the only difference is doubling the rate of A, the concentration of A, doubling the concentration of A, doubled the rate, so that meant A was first order. So I determined experimentally that A was first order. So here's a scenario where I keep the concentration of A the same, and I double the concentration of B. So concentration of B was doubled. Let's see what happened to the rate. I have 6.0 times 10 to the negative fourth, and I have 2.4 times 10 to the negative third. That is a factor of 4. The rate quadrupled. When I double the concentration of B, the rate quadrupled. That means this reaction is second order with respect to B. And I can write the rate expression as K times the concentration of A, because it was first order, times the concentration of B squared, because B was second order. And there you have it. So a summary of this is if I double A and there's no change, that is 0 order. If I double A and the rate doubles, that is first order. If I double A and the rate quadruples, it is second order. But if I tripled A and I got no change, then it's 0 order. If I triple A and the rate triples, it's first order. If I triple A and the rate goes up times 9, because 9 is 3 squared, triples is times 3, 3 squared, that's second order. If I have a 4-fold increase in the concentration of A, so that's times 4, and there's no change, that is 0 order. If I quadruple the concentration of A and the rate increases by a factor of 4, that is first order, and 4 squared would be 16, so a Second order reaction, if I quadruple the concentration of a reactant, it would make the rate of the reaction increase by a factor of 16. Crazy. Checkpoint question. Take a look at the question. See if you can figure out the reaction orders with respect to NO2 and with respect to F2. Pause the video and come back for an answer. All right, the answer is C. Second order for NO2, first order for F2. And so let's take a look and see if we can figure this out. If you got the right answer and you want to move on, fast forward a little bit. When I kept F2 the same and I doubled NO2, the rate quadrupled. So that meant that NO2 was second order. When I kept NO2 the same and I doubled F2, the rate doubled. So that meant F2 is first order. And so that means C is the right answer. I hope that description was helpful for you. A little checkpoint question. Please make sure you're filling in the Google video or the Google form on the Haiku page, because I want to know if you're getting this right and if you need me to explain it again or give you a new example to give you a little bit more practice. And that's pretty much it. We'll do a few little wrap-up items here. International mindedness. The first catalyst used in industry was for the production of sulfuric acid. And sulfuric acid is an amazingly important chemical for a lot of reasons. And sulfuric acid production closely mirrored a country's economic health for a long time. What are some current indicators of a country's economic health? Who knew that chemistry and economics could be so closely related? TOK, reaction mechanisms can be supported by indirect evidence. What is the role of empirical evidence in scientific theories? Can we ever be certain in science? And the nature of science. The principle of Occam's razor, the simplest explanation is often the most likely. As a summary, the rate expression can only be found through experiments. And data from rate experiments can be used to determine the order of reaction with respect to individual reactants and thus the order of the overall reaction. You made it. That was a bit of a long video. I appreciate you hanging in there till the end. Please take your time to fill out the survey so that I know how you did on the multiple choice question, checkpoint question. Of course, you can provide feedback if you'd like and rate the video. Thank you for listening. Have a great day. I'll see you in class.